Welcome to the Explainer. We are jumping right in today because we're decoding series and parallel circuits, too, and we're tailoring this specifically for the Cambridge IGCSE 0625 syllabus. But hey, don't worry, we're absolutely not going to just sit here and run through a dry, boring list of equations. Where's the fun in that? Instead, we're taking a really powerful concept-first approach. We're going to break down the core structure and look at the first principles explanation for how circuits actually work. So, whether you're chasing those top exam marks or you just want a rock-solid grasp of the underlying physics, this structured approach is literally going to change how you look at electricity. Let's get started. Section 1. The Circuit Challenge. Making physics feel necessary. Okay, let's dive into this. One of the biggest mistakes we see in physics learning is starting straight out of the gate by just memorizing formal, highly decorative language. We memorize the formulas, we memorize the definitions, but we completely miss building an actual intuition for the science, right? So a truly strong lesson needs to start by making the core ideas feel absolutely necessary. We have to strip away all that complex wording first and ask ourselves one fundamental question. What physical effect, measurement, or prediction actually depends on understanding these circuits? Grounding the topic in a real physical necessity, that is your secret weapon here. It completely prevents that terrifying dependency on memorized wording. Because think about it, when you inevitably face a super tricky, unfamiliar exam question, if you understand the actual physical effect happening in the wires, you can reason your way right through it, rather than just crossing your fingers and hoping you remember a specific textbook sentence.
Section 2. The four-step core, moving beyond rote memorization.
And this brilliantly illustrates why this micro-topic of series and parallel circuits isn't just some isolated chapter you can forget about later. It actually acts as a massive gateway into a much bigger scientific pattern used across all of physics. To truly master it, we use these 4 linked steps to absolutely secure those top marks in IGCSE-style physics. First, you identify the quantity or phenomenon you're looking at. Second, you explicitly state the relationship involved. Third, you explain the underlying physics, like the actual mechanics of what is happening under the hood. And fourth, you connect it to an observation, an experiment, or a real-world device. This sequence is absolutely vital. Why? Because the very best exam answers always show a perfect blend of both deep understanding and practical application. Section 3. Cause and Effect Physics. Mastering the vocabulary. Let's move on and see how this builds. To properly chain these physical ideas together so they make actual logical sense, a strong explanation has to start with a tangible, concrete, everyday example. You've got to begin with the real world. Only when that everyday foundation is rock solid do you build a bridge to the formal physics vocabulary and those abstract symbolic relationships. And then, once you have that formal language firmly in place, you return right back to a worked explanation. Doing this builds a permanent bridge in your mind between the abstract math and the actual physical reality. It's a real game changer. I absolutely love this quote from our source material. Insist on cause and effect rather than isolated facts. It hits the nail right on the head. Whether you're discussing fields, forces, particles, waves, or, in our case, circuits, your focus must always be on unbroken causal chains. Look, physics is not a trivia game of disconnected facts, not at all. It's a continuous chain where one physical action directly, inevitably causes a specific reaction. And this causal reasoning directly applies to how we handle data, too. If graphs are involved in a circuit question, you cannot just look at the line and call it a day. You must explicitly state what the graph means physically. What does the slope represent in the real world? What physical quantity is the area under the line? What does the direction tell us? What does the overall shape reveal about the circuit itself? Connecting that abstract visual data right back to the concrete physical meaning is essential, for sure. Section 4. Real-world applications. Physics outside the classroom. Now, what's really interesting here is that everything we've structured so far pushes right out into the real world. This is exactly why this microtopic is so immensely useful. The concepts embedded in series and parallel circuits critically appear everywhere, in experiments, complex engineering, crucial safety mechanisms, modern transport, global energy systems, communications networks, advanced medical technology, and, get this, even astronomy. The principles governing how current flows and splits are truly universal, no matter the scale or the field you're looking at. Because of this massive real-world presence, you should always be prepared to name at least one real situation where the concept matters. And more importantly, you need to be able to explain exactly why the physics helps us predict or improve outcomes in that situation. If you can clearly justify that physical link between the circuit theory and a real-life application, you prove to the examiner and to yourself that you truly own the knowledge. Section 5. Avoiding exam traps, where students lose marks. But, of course, applying this knowledge under the pressure of an exam is where things can easily go wrong. To avoid these traps, we rely on the absolute safest method for structuring exam answers, which directly echoes our earlier core steps. It's a rigorous four-part sequence. You start with the definition. Then you move to the relationship. Next, you provide the explanation of the physics. And finally, you finish with the application. Sticking religiously to the structure keeps your answer perfectly anchored and logical. So, what happens when you stray from that structure? Well, let's pull out the red pen for a second. The source highlights 3 highly common weaknesses where students just unnecessarily lose marks. First, writing down a perfectly correct formula but completely failing to explain what the variables actually stand for in that specific scenario. Second, coding a physical process accurately but forgetting to link it back to the tangible physical effect it causes. And third, throwing in a great real-world example but failing to show exactly why it follows from the physics you just explained. Every microtopic you study needs to be tightly connected to your classroom reasoning to counter these exact errors. Don't fall into these traps. Section 6. The Quick Recall System, Securing Your Knowledge.
So the crucial point is how we actually lock all of this in before test day. This right here is your ultimate revision tool to make sure the knowledge is secured. When you sit down to revise series and parallel circuits 2, use these 4 specific prompts. 1. What is the core idea? 2. What changes physically in the system? 3. What specific quantity or graph visually shows this change? And 4. Where is it practically used? The rule is incredibly simple. If you can answer these 4 prompts aloud, comfortably, and confidently, your understanding of the topic is usually secure enough for even the absolute toughest short answer and structured questions.
So, I'm going to leave you with this final provocative challenge. Can you explain the cause and effect chain of a parallel circuit aloud right now using those 4 quick recall prompts? Seriously, don't just think it in your head, speak it out loud. Test your true grasp of the material. Because if you can do that, you're not just memorizing physics anymore, you're actually speaking it. Thanks for joining me on this explainer, and remember, keep questioning the physical world around you.